Hello and welcome again to my physical science online video supplement series. Today's video is for the physical science labs, and what it is going to be is another of my lab walkthrough with examples videos. This one is to go with the pendulum lab. So let's go ahead and pull up the instructions for the pendulum lab. This is your handout for this lab, Pendulum Lab Experimental Procedure. There's a few pieces of information to note at the beginning. For example, we're going to use the gravitational acceleration g equals 9.8 meters per second squared throughout. And it is worth noting that this is going to appear somewhere in the slope of one of your graphs, and it can be found using dimensional analysis. So before you begin the lab, you may want to make sure that you have all this equipment. You will need something with which to measure the length of your pendulum. You will need a string, which is to be lightweight and strong. I recommend fishing line for this, but you can get away, depending upon what you're using as your weights, you can get away with thread, you can get away with dental floss. In fact, dental floss probably works pretty well for this. And you're going to need something to hang the string from. If you happen to have like a shed or a barn or something with a rafter, that works out nicely, or in the attic of your house, a rafter is fine. A branch from a tree would work pretty well for this. One way to do it is to put a screw eye into the ceiling or into the rafter or what have you. You can hang the string from that. You're going to need to have some weights. I actually, when doing it on campus, would use just a standard set of weights. Basically, something like this is what we use on campus. In fact, it is this exact weight set by Pasco, although something like this would be fine as well. Also something from Pasco, etc. You, however, may not want to spend so much money for a weight set like this that you're probably going to use once or twice, depending on if you bought something like this for the Springs lab. I wouldn't blame you if you said I don't want to do that, so you may try something else like a water bottle or a water balloon that you can add some water to. In fact, a water balloon would work very nicely as long as you know how much water you've added to it by mass. You're going to want a protractor, and you're going to want a stopwatch of some sort. Obviously, you can use your cell phone for that if you don't have a stopwatch otherwise at hand. And so what are we going to do in this experiment? Well, the point is that we're looking to see what it is that the period of a pendulum depends upon. So what does a period represent? Well, it basically means the amount of time that it takes to complete an entire swing. I've already shown this in a previous video, but just to give a nice diagram of what this might look like, you've hung your pendulum. If you just leave it alone, it would be hanging vertically. Instead, you pull it away from the vertical by some angle. So the pendulum I'm going to represent as a long string and a short mass. This right here is your initial angle. This right here is the mass, and this right here has length L, and that length is actually from the center of this mass to the point where you are hanging this from. So what will happen is when you've released it over time, the pendulum will begin swinging. So if initially you released it from this initial angle, after a little while it might be here, and then after a little while longer it'll be vertically like this, and then a little while longer it'll be hanging over here, and then eventually it hits sort of a maximum displacement on this side. This drawing is not quite to scale because in fact this angle and this angle should be the same for the maximum displacement. Then it ends up swinging back, duplicating each of these, and eventually it ends up back over here. And as soon as it gets back over here, the amount of time that it takes to have swung from here over to here and then back, that is one period. So we represent that with a big T. So big T represents period, and that is time for one whole swing. And so that is what you're effectively trying to time for. Now, again, if you watch the other video, or even if you didn't watch my other video, if you just try this at home for most strings, most pendulums, most string lengths, you'll find that it gets to here and then comes back in a very short amount of time. Often T is less than 1 second. In fact, if you want to have a period of about 1 second, then you need to have a pendulum length of about 1/4 of a meter. So T is roughly 1 second for L, approximately 0.25 meters. In fact, it's just slightly shorter than 0.25 meters for what that's worth. So this is a pretty fast amount of time, especially if you do any for shorter than this length. And you have some reaction time. That reaction time is something that you actually kind of sort of measured in the first lab when you dropped the meter stick. It's a little bit different for if you're using a timer stopwatch because you have a visual stimuli that you're using. You're pushing a button, then waiting until this thing is completed a whole swing, and then pushing the stop button. But let's assume, for the sake of argument, that you have a reaction time of 0.2 seconds. If that's the case, you'll notice that this reaction time is a substantial fraction of this period. In fact, it is approximately 20% of the period. And again, you're actually both starting and stopping the stopwatch with some relationship to when you've released this pendulum and when it swings back. So in a sense, you have this reaction time on both sides of the period. So depending upon how lucky or unlucky you are and how good your reaction time is, this could actually be as big as a 40% error for a 0.2 second reaction time on both sides. In other words, if you start it a little bit fast and you have a 0.2 second reaction to release the pendulum, and then you stop at 0.2 seconds slowly from when the pendulum swings back, you're going to have 40% error. Probably it's more reasonable to say that you've got about a 20% error on average, because you're likely not going to make that exact sequence of errors. With that said, this is still a pretty substantial amount of error. So one thing that we're doing to fight this is you'll notice that each swing that the pendulum makes takes the same amount of time. And in the event that you're not 100% convinced of that, we even take some data to kind of sort of show that. Namely, you take data on how this initial angle of displacement affects the period. And you'll find that it does not. That's stated in the directions. So what we do is we allow this thing to swing back and forth many times. Let's say that we allow the thing to swing back and forth 20 times. So with 20 whole oscillations, perhaps you get a total time, we'll call it T sub t for total time, of, I don't know, maybe you time it and you get 25.0 seconds. That's the total time to complete these 20 oscillations. So what you're wanting to get is the period t, which again is the time for one oscillation. So how do you do that given this set of data? Well, you can use basically that the total time is the number of oscillations times the period for one oscillation. So by implication, the total time to do one oscillation, in other words the period, must be the total time that all 20 oscillations took divided by the number of oscillations, namely 20. So you'd have 25.0 seconds divided by 20 oscillations. You can write in oscillations here if you want, but the period has final units of seconds because it's a time. So you could put time per oscillation if you'd like as your unit. T therefore is 25 over 20. So how many times does 20 go into 25? Well, you can use your calculator or you can do long division or what have you. You can see that it goes one whole time and then there's a remainder of 5. 5 is a quarter of 20 because 5 goes into 24 times. So that means that 20 must go into 5 a quarter of a time. And so your period must be 1.25 seconds for this little example. So you may be wondering, why is it that we went through all of this? Well, instead of just timing one oscillation. Well, again, this was 20% of your 1 second time, or with respect to this, it's maybe a little less than 20%. It is about 16%. So this would be 16% of the period. But the truth of the matter is that this reaction time only really gets you once at the beginning and once at the end of when you start and stop the motion. And again, on average, that basically works out to about once at the end when you stop the motion. So the time that we actually went for was 25 seconds here. So while this is 16% of t, in other words, if you've just done this one time, you might expect anywhere between, say, 1.09 and 1.41 seconds. For this right here, the range that you would get is maybe between 24.8 seconds to 25.2 seconds. Again, the range is about the same. This one would have been, 1.05 seconds to 1.45 seconds. I'm basically subtracting 0.2 from this number, and then I'm adding 0.2 to this number, and then ditto for this one. So you can see, again, this is plus or minus 16% of the period, but what fraction is it of the total time? Well, you can do that basically by putting 0.2 and dividing by 25, and then multiplying that number by 100 to get the total percent. And if you do that, what you find is that this is actually about 0.8% of the total time. So instead of having a 16% error, we've just reduced ourselves to having about a 0.8% error for this particular pendulum. So that's why you want to time over many oscillations. So what you would do is you'd pick your number. Again, I picked 20. And so you pull the pendulum back to whatever angle you're supposed to, say 10 degrees. You release it. You start the stopwatch when you're releasing it. You let it swing 20 times without pushing any buttons on your stopwatch. You just count out to 20 swings, and on the 20th swing, you push stop. That's how we got this total time. That's how we got this number of oscillations. You divide the two, and now you've got the period. Okay, so what else is it that we need to do here? Well, that basically is going to cover this whole summary of the experiment, this discussion in here about your error. So now let's look at the actual experimental instructions. And it looks like for the experimental instructions, what we're going to do is we're going to choose 3 different masses. So again, this is why I think maybe buying the whole Pasco mass set to do this at home is maybe overkill. You could just use 3 water balloons. What you do is you pick a mass. Let's say that you decide to attach a water balloon with 300 grams worth of balloon plus water in it. You attach that to the end of your string, which has a length of 1 meter, and you use an initial displacement of 10 degrees. So let's label that. Basically, to draw it out, it would look like this. So here's my string. Here's my water balloon attached to the end of the string that has 300 grams in it. This length is 1 meter long. Maybe be easiest to measure it with it hanging vertically, by the way, but it'll still be 1 meter long either way. And I've pulled back by 10 degrees. So you've got to use your protractor to measure off 10 degrees here. So then you release this thing, and it makes however many swings you've decided to pick as your number in. And you time it. You'll get some number. And note that the instructions basically just say time enough oscillations so that you have greater than 10 seconds with this mass. So you time until you have more than 10 seconds worth. And again, my recommendation here is that you pick a number of oscillations, not a total time that you're shooting for, because it's easier to figure out what happens if you have 12 oscillations, for example, than if you have 10 seconds but you were 2/3 of the way through an oscillation when those 10 seconds occurred. So in any case, do your 12, 20, 10, 15, however many oscillations you've picked, and get the period. So the math then is the same as what I just did in that example. Maybe you do 20 oscillations, you get 25 seconds or whatever, you get 1.25 seconds. That example, by the way, is probably not going to be correct for 1.0 meter and 300 grams and 10 degree angle. So you're going to have to do your own here. But in any case, you're going to do this for 3 different masses. So the one I just drew was maybe for my first mass, 300 grams. And with 300 grams, what that means is that you actually have 0.3 kilograms. Hopefully you can at least get 2 significant figures in there. Okay, so now the instructions say that you're supposed to do this for 3 different masses. So maybe you would repeat for 500 grams or 0.50 kilograms. And you could also repeat for some other mass. Maybe you decide to go with 100 grams or 0.10 kilograms. Notice, in case you're having trouble with this point, that 1 whole kilogram is equal to 1,000 grams. So if I want to go from grams to kilograms, I just need to have this decimal. 100 has a decimal here, 500 has a decimal here, 300 has a decimal here, and I have to move it over 1, 2, 3 times to get it into kilograms, which is the same as dividing by 1,000. Alright, so you do this for the 3 different masses. You get 3 different periods, and you will maybe do this a second time. So repeat period 1, period 2, and period 3. So you'll go back through with 300 grams, 500 grams, and 100 grams and time it a second time. By the way, you may want to do this by basically doing 100 grams and then doing 100 grams again. Then do 300 grams and 300 grams again, then 500 grams and 500 grams again. That way you're not having to tie and untie the balloon a bunch of times, or fill and refill the balloon a bunch of times if you're using a water balloon. The next thing that we want to do is look at the angle and what effect the angle has. So notice that up here we were doing for a 10-degree angle. So that means that you can basically copy the answer that you had from up here for the period here and the period here. You're using mass number 2, which as I drew it would probably actually be the 300 gram mass. Basically you want whatever is the middle of the two masses that you chose, even though I did 300 grams first. In drawing it, I decided we had 100, 300, 500, so use the 300 gram mass in my example. So you'd basically be copying this number and this number to put in here and here, because you've already done that. So then you go and you change the angle to 15 degrees and you repeat with that 300 gram mass twice, and then you change from 5 degrees to 15 degrees, you repeat twice. So that basically means that you pull this guy out to only 5 degrees, which means it's down here somewhere, and you pull out to 15 degrees, which means it's probably over here somewhere. Okay, so now you have finished the checking the effect of the mass, checking the effect of the angle. If you've done everything right to this point, what you will notice is that not only does the mass not have much of an effect, but the angle does not have much of an effect either. In fact, here it says that explicitly in your directions. And the significance to the angles not having any effect on this is that this whole timing over many periods thing actually will work. If the angle actually affects the period, then timing over many periods doesn't actually work, because you'll notice as the pendulum swings back and forth, the angle that it reaches, the maximum displacement, actually gets a little bit smaller, so that if you let it swing for long enough, eventually the motion basically dies down to 0. Hypothetically speaking, though, I could have, and in past terms I have in fact done this, we could have done this with many more masses, say a set of 9 masses and a set of 9 different angular displacements. And we could have then made graphs of period versus angle and period versus mass. So the question is, what would that look like hypothetically if we were to do that? So first of all, if you're going to be making a graph, you should use some graph paper. Now I don't care if you're going to use actual graph paper that you've bought at the store, or whether you go online and find graph paper that you print off. If you type graph paper into Google and look under images, you'll find plenty of different examples that you can just print. Or you can use something like Excel or LibreOffice or OpenOffice, the latter two of which are actually free. And you can make graphs that way, or MATLAB or Mathematica, or however you want to make them. So how would we make this graph? Well, for starters, what we do is we set up our axes. So this one would be the period axis. This one right here would be, let's say, the mass axis. And we want to have units, so mass is in kilograms, period is in seconds. You'd have to have some data to do this. All right, let's say that we pick our masses to be between 0.1 and or between 0 and 0.4 kilograms. So we would be basically labeling these long guys by increments of 0.1 kilogram. And maybe we end up getting our period labeled like this. Since our axis is labeled in seconds and in kilograms, we don't have to put the unit a second time. Now let's say, for the sake of argument, that you have a mass and you have a period. And again, this is in kilograms and in seconds. So perhaps our mass versus period, you have a little table, and the little table says 50, 100 grams, 150, and then 200, 250, 300, 350, and 400 grams. So that's what they'd look like in kilograms. Now maybe you did this and you get times like, let's say 1.01, 0.98, 1.05 or whatever, 1.04, 0.99, 1.00, 1.03, 1.04. So maybe that's what your periods look like. So what we do is we plot all these points over here. And given the increment size here, this would be 0.25, 0.5, 0.75, 1. And over here, this one is the 50 gram, this is 150, this is 250, this is 350. So given that, all these periods are pretty close to 1. So we'd have, for 50, we'd have maybe just a little bit above that 1. And then for the next one, we're a little bit below. At 150 grams, I was a little bit above. At 200 grams, I was also just a little bit above. At 250, I was just a tad below. At 300, I was right on the 1.00 seconds. At 350, I was just a little bit above it. And at 400, I was also just a little bit above it. So this right here is an approximation of what my graph might look like. So what I need to do at this point is basically draw a line of best fit. Now I don't have a way of putting a ruler on my screen here that I can follow easily, but what you would want to do is use a ruler to make sure that you're getting a nice straight line. You set up your ruler and you do your level best to draw a nice straight line of best fit. And so that would be my line of best fit given this set of data. You'll notice that this line is basically what looks to me like a horizontal line. So a horizontal line has a slope of 0 because the rise is 0 and the run is more than 0. So hypothetically, if we were drawing a line of best fit graph for angle and for mass, initial angle and for mass, we'd get something like this. However, with only 3 data points, it's awfully difficult to tell that that's what's going on. In fact, you can make a decent line of best fit for 3 data points, but you can make an exact parabola of best fit for any 3 data points. There will always be a parabola that you can fit through 3 data points. And any higher order polynomial you can also fit perfectly through 3 or more data points. So we're not really going to be doing this graph, but I thought it would be interesting for sort of this is what your graph is going to look like illustrative purposes. All right, next up we have this part where we're varying the length of the pendulum. So you're going to do 9 different initial pendulum string lengths. You're going to use the middle mass and the middle angle of displacement to do this. So you've got to pick out some lengths, and you'll notice that there's basically 9 columns or 9 rows, excuse me, that you can fill out, and then I filled out a 10th one. The time row is for you to get the total time for however many oscillations you choose. In the case of my example, I timed for 20 oscillations. And so you're going to do a time column, you're going to do a period column, this divided by this, and you're going to do a period squared column, this number squared. So let's look at the example piece of data that I've included for you, just for illustrative purposes. So I gave you a length L equals 2.50 meters, and I had a time, or the equivalent of a total time, of 63.470 seconds, and this is for n equals 20 oscillations. So those are the first two columns. You measure both of those. The period t, again, is the total time divided by the number of oscillations. So that would be 63.470 divided by 20. So plugging this into the calculator, I have 63.470 divided by 20, and that gives 3.1735. So this is 3.1735 seconds. And you'll notice that that is in fact what I have put in to this period. So this you measure with your stopwatch. This is your first calculation. Now we do the period squared. So the period squared thing would look like t squared equals 3.1735 seconds squared. That's the same as 3.1735 seconds times 3.1735 seconds. So I can actually throw that into the calculator. Again, there's actually a squared button, so we'll push that. 10.07110 blah blah blah. We don't need quite that many significant figures, so this would be 10.07, and since there's a second and a second, the unit is seconds squared. So that is where this last column is coming from. Okay, now what you have left is two steps. One is that you make a graph that shows the period versus the length of the pendulum. So I'm not going to try to draw that graph just now. I have a whole separate video in which I talk about not only this step but also the squaring an axis step. So you could think of this as your period big T, and you could think of this as period squared big T squared. That's essentially what we're doing here. So you're going to end up making two graphs. One of them is going to basically have on the this axis you'd have period, or T, and on this axis you'd have length L. So this is in meters, this is in seconds. For the second graph, you end up having period squared in seconds squared versus length in meters. And you could also try what happens if you put the period in seconds versus the length squared in meters squared. So I will try to sketch what those three look like, although these are rough sketches. Basically, the first one is going to be a sideways parabola. So something like that. The second one is going to look more like a nice straight line, like this. The third one is basically a sideways thing to the fourth power, so it's going to curve more dramatically, like this. So of these, the one that's actually useful is the one that makes a line. And so once you have a line, the next step is that you find the slope of that line. So you pick 2 points that are on the line. I just picked 2 points that are on the line. Your data points might actually be more like this. This is maybe more data points than you actually have, but maybe that's what your line of best fit ends up looking like. Similarly, for the red one, you might have something more like this. You know, nothing's actually on the red. And for the blue one, you can have like this. And in fact, you'll notice when you actually do this that there is one big discrepancy between what I drew and what you'll get, which is that the spacing between points is going to change so that they line up to make a line. Here, if you did everything evenly, you're going to get some evenly spaced points in the x direction. This one, you're going to find that a bunch of the points are clustered and then they get a little farther apart as you go. In any case, you can find the slope using basically the rise divided by the run. The run actually is the horizontal distance, so probably it would be better if I drew the run more like this and the rise more like this. But it's this distance over this distance, keeping in mind that you are using a scale here. This distance may, in other words, represent 2 meters, or it may represent 1 meter, or it may represent 0.5 meters. You have to look at your scale. In any case, there's a whole separate video just on this topic, so you can go watch that one if you still are not clear on how to square the axes. But what you should find when you do this is that the slope is somehow related to the gravitational acceleration g. So slope and g are somehow related. This is, of course, 9.8 meters per second squared. And what you want to do is try to figure out how they're related. The hint that I'm going to give you is that there are units for this slope. Units will be units of y divided by units of x. So look at your y-axis, look at your x-axis. The units of these, that's going to give you your slope units. So you want to look at what these units are, and then you want to look at what units go with this guy. And from that, you may be able to make a guess as to how the slope and g are related. Note that there may be an additional constant that is unitless that goes into all of this, but that's as much as I want to say about that. So hopefully you found this video to be helpful in doing this lab, and good luck. Thanks for watching.